quantum mechanical, there is a regime where there is no obvious magnetic order to be detected numerically. Okay, so what did we do? Well, we were looking for a method to calculate the spin correlations, or exactly the spin susceptibility as a function of momentum. A method to calculate this in an unbiased way, without putting in, some prejudice as to this or that state. And such an unprejudiced way is a renormalization proof calculation. Because a renormalization proof calculation has the advantage that it captures all the terms in all the channels, at least in weak coupling or maybe intermediate coupling. But how to do that for a spin system? Well, you first have to transform the spin system into a Fermi system. Okay, so this we do by representing the spin operators in terms of Fermi operators here. So the F's are the Fermi operators, these are the Pauli matrices here. So it can be done in this way. There's a little problem here, there's actually not a big problem in this context, namely that for spin 1/2 you have two states, up and down. For the fermions, if you introduce these fermions, you have four states. You have spin up and spin down, you have empty side, and you have doubly occupied side. And obviously you have to get rid of the empty side and of the doubly occupied side. That's easy, because at low temperature or low energy, the empty and the doubly occupied side cost energy. They cost energy of the order of the exchange coupling, exchange energy. So if the temperature is much less than the exchange energy, these unwanted states are projected out exponentially. So we don't have to worry about it. So we can use a simple constraint here, which is that the average Q is equal to 1, which means that the chemical potential of these fermions is equal to 0. Okay. So now we have a fermionic system, and now we can apply functional renormalization group theory to this. Of course, I cannot go into detail, I just want to show you roughly how this works. The functional renormalization group method has been invented in particle physics, of course, about 25 years ago. And it works in such a way that you generate renormalization group equations for all one-particle irreducible vertex functions, infinitely many. So this will generate a hierarchy of equations, infinitely many equations. First equation is for the self-energy here. Next equation is for the usual vertex function. The next equation would be for this vertex here, and so on. Of course, we cannot solve the infinite hierarchies. We have to truncate this system. So we truncate here, take these two equations, but we take this term into account by using the self-energy type corrections here. And it turns out that this is enough to give excellent results. So we can calculate, as I said, the Q-dependent, K-dependent susceptibility. So for instance, at the G value of 0.2, where we expect an Néel order, we find that at K equals pi, which is the usual Néel antiferromagnet, the susceptibility starts to increase, so that signals the ordered state. Then at some point this will break down, so we don't have to take this seriously, whereas the collinear K value stays here. For large G, the collinear susceptibility increases in the other one, stays low. And in the middle, for say 0.55, we see that we can actually go with our renormalization group parameter all the way to 0 for all the k's, and no order is formed. Chi never diverges for any k. That does not mean that there is no order of some kind at all, but at least there is no order of the conventional kind in the system. Okay, good. Now we have also looked for other signatures like Plaquette order, dimer order, and so on. But this search, I have to say, was not successful, so we cannot be absolutely sure what the order is in this case. Now the next interesting case is the so-called Heisenberg-Kitaev model on the honeycomb lattice. Why is that interesting? Well, that's interesting because of a enormous breakthrough about 10 years ago, 2003, when Kitaev showed that there is a model on the honeycomb lattice, an anisotropic spin model on the honeycomb lattice, that has an exact spin-liquid ground state. He was able to solve this model analytically. So we have one absolutely fixed result here, and that is in this model. If J1 is equal to 0, we have only this term, which is a very strange anisotropic spin interaction, namely which has the structure that along the bond ZZ, so we have three types of bonds, X, Y, and Z. Along the ZZ bond here, the coupling is only SC. And along the XX bond is only SX. So it's a highly anisotropic bond, Kitaev bond. And there we know that we have a spin-liquid state. Whereas for alpha equal to 0, so which means that this term is 0, we have the usual Heisenberg on the honeycomb lattice, which has some order. Okay. So the question is now, of course, how can we realize this in a compound, in an experimentally accessible compound? Okay, let me first tell you what the FRT calculation gave for this model. So, so it gave this antiferromagnetic state for small alpha, so when the Heisenberg term dominates, gives so-called stripy antiferromagnetic phase in the middle, which is here and here, so you have two big peaks here and two small peaks here, and no peak beyond, say, 0.8, which must be the spin liquid. So in this calculation, the spin liquid is recovered, and now we may ask, what do we have to do? In which compound can we get a realization of this model? Okay? The compounds that are most promising are iridates, so iridium oxide compounds, and that is because these compounds are multi-level systems. Multi-level systems means that there's not only a Coulomb interaction between the electrons on these levels, but there's also a Hund coupling between electrons on different levels. And that's important for the anisotropy of the spin exchange interaction. And the other ingredient is that the iridates have a very strong spin orbit coupling. And that's also good for anisotropy. So it has been suggested in this, Okay, it has been suggested in this calculation, these people, that one may add large J2, second nearest neighbor and third nearest neighbor couplings, Heisenberg couplings, in order to be able to explain the observed zigzag phase. So experimentally, in this iridates, one observes a spin configuration of this type here. And this, as you may remember, did not come out of the previous calculation, one slide back. So we have to do something to get this zigzag phase. This is what they did, okay? But these couplings J2 and J3 are much too large. And we have recently been calculating this coupling from microscopic theory, which is not too hard. And we find that there's another thing happening, namely the second neighbor Kitaev coupling is very large. And it's ferromagnetic. It's antiferromagnetic. There's the nearest neighbor coupling is ferromagnetic. The second neighbor coupling is antiferromagnetic. And if you look at the phase diagram that we determined in just classically to get some idea, if this K2 term is 0, you get what was found on the previous slide, and then you get this stripy phase here mostly. Whereas if this K2 is as large as we calculate it to be, you get a large portion of the phase diagram to be a zigzag phase. And experimentally, you would be here over here. Okay. So this means that the prospects for finding the spin liquid phase in these compounds is not too good. And I think we have to do some more work to get other compounds which have an even more anisotropic interaction, but we are at it and we will discuss this. Okay, let me now move on and come to the next point, namely fractional quasiparticles in one-dimensional systems. Strictly one-dimensional systems. Not quasi-one-dimensional systems, but strictly one-dimensional systems. Theories for one-dimensional systems were formulated a long time ago, starting in the 1950s, Tomonaga, and then later in the 1960s, a lot of people. And they were considered because they are mathematically more accessible than theories in 2 and 3 dimensions. And there was mainly one method that was developed, and that's the method of bosonization, which means that in a one-dimensional system, under some conditions, you can map the system onto a boson system, and this boson system can be exactly solved. That's a big advantage, and it has been used. The only problem was there were no one-dimensional systems in nature up until a few years ago. Now, with the advance of nanoscience, we have one-dimensional systems. One prominent example is carbon nanotubes, which are little tubes made of carbon, which have exactly one channel, or maybe 2 channels because of the spin, but they are exactly one-dimensional systems. And these systems can be used to do experiments and to measure transport properties, and that's what I'm going to show you. Okay, so first let me summarize what has been known for a long time. So what happens to the Landau quasiparticle in one dimension is that it breaks up into 2 quasiparticles, namely a charge part called chargon and a spin part called spinon. And if you look at the single particle spectral function, A of omega is a function of omega, then it's no longer characterized by one peak or one quasiparticle peak, as in Fermi liquid theory, but there are 2 peaks. One for the spinon and one for the whole or charging. And these are located on different energies because the velocities of these 2 quasiparticles sort of are different. So spin and charge propagates at different velocity. Okay. Now the problem with the bosonization method is if you want to calculate the transport properties of a one-dimensional system, that the one-dimensional system is contacted through reservoirs. Of course, when you have carbon nanotube and you have two gold blobs that it makes contact with, you don't have an infinitely long one-dimensional system. And the results that were obtained, most of them were for the infinitely long system. So here you have to make sure that if a particle, an electron gets into the 1D interacting system, that it's really one electron. Of course it will, in bosonization language, it will split up into the bosonic excitations, but that's not very convenient to calculate. So what we did was to use a regularization group treatment for fermions only, which is based on an infinite order perturbation theory. And so far, the results of this theory, they produce known fixed point structures and new fixed point structures, critical exponents, quantitatively correct conductance, as I said, in contrast to the bosonization method. And this has been used to compare, to describe an experimental carbon nanotube junction. So the carbon nanotube is this little thing here that's crossing these electrodes here. And they measured the conductance G as a function of a gate voltage. And our theory is sketched here. So G is the conductance, and T is the temperature, and T naught is a quantity that depends on the gate voltage, which would now change if you change the gate voltage. And if you use this expression here, you can fit the experimental data very nicely. And this has fractional power law behavior here in this function. These are the charge modes of the system. Okay. Let me now I have to speed up a little bit, I think, to the third example, which is quasiparticles in the quantum Hall effect. Now, you all know, I think, the sort of most important facts about the quantum Hall effect. It was discovered in the 80s, and the fractional quantum Hall effect was discovered by these people here. The theory was done by Volfle mostly. Nobel Prize is given for this. And what is it? Well, it's a measurement of the transport of a strictly two-dimensional electron system. So the strictly two-dimensional electron system is done in the semiconductor heterostructure, so in the aluminium gallium arsenide system. So we have a completely, exactly two-dimensional system here, and it's contacted in ways with these contacts here. You can measure the longitudinal resistance and the Hall resistance. And what is found is this astounding behavior, that the Hall resistivity as a function of magnetic field does not follow the expected classical behavior to be a linear function of magnetic field, but it shows steps. And there are two kinds of steps. There are steps that appear at filling factors, come to the filling factors of lambda levels, 1, 2, 3. This is the integer quantum Hall effect, where Rx is 1 over the filling factor times RQ. And when the Hall resistance has a plateau, the longitudinal resistance is exactly 0. At higher magnetic fields, we have fractional quantization, which is 1 over some fractional filling factor times the quantum of resistance. And these fractional fillings have a peculiar structure. And it follows this form here. So P is integer 1 plus minus 2 and so on. And Q is an integer 2, 4, 6. And all of these plateaus fit into this scheme here. Okay, let's first look at the integer quantum effect. What happens when a two-dimensional electron system is put into a magnetic field? Well, without the magnetic field, it forms a Fermi sea here. The magnetic field is applied. The spectrum goes over into a discrete spectrum of Landau levels, which are filled according to the size of the system and so on. And in the extreme case, only the lowest Landau level is filled. How does that help to explain the integer quantum Hall effect? Well, first of all, we have to say that at a relatively large filling factor, the Coulomb interaction between the electrons is well screened and is negligible. So the situation is much, much simpler than what I discussed for the most part before. We have a non-interacting system and the electrons in the interior of the whole bar are localized by disorder. So there's always disorder in the system. And if you imagine the quantum Hall state as sketched here, so in the high magnetic field you have these cyclotron orbits here, and if there would be nothing else, these orbits would drift, of course. But because of the disorder, they are locked in place. They cannot drift. Instead, you have transport at the edges because you have the skipping motion states, which provides a chiral transport in one direction only along the edge of the sample. So if you look at this in energy, then you have a valence band, a conduction band, the Fermi energy is somewhere in the middle, so they have an insulator here in the middle, but these states form a line of states, the edge states. And what you get then is that you have electrons propagating along the edges in this chiral way as sketched here. And this will give you a quantized resistance because this transport is uninhibited by disorder because electrons can only move in one direction, so there's no backscattering. You can have as much disorder as you want here, it doesn't matter. Electrons can never go back. So you get this quantization, and if you have several of these states, because you have several Landau levels, you get 1 over nu is 1, 2, 3, and so on. Okay, fine. But how to interpret the fractional quantum Hall effect? Now this can actually be done in a way that is not, I would say, theoretically not completely understood, but it works perfectly well. And that is the composite fermion picture. So what apparently happens is that an electron captures 2 flux quanta and forms a new particle, which is still a fermion. It's called a composite fermion. Now, if it captures 2 flux quanta, the remaining flux is of course much weaker than the initial flux. The remaining magnetic field, B effective, is the original field times 1 minus 2 nu, where nu is the filling factor. And if the filling factor is 1/2, then 1 minus 2 nu is 0, and the effective field is 0. So these composite fermions at half filling behave as if they were, just a Fermi liquid in the absence of a magnetic field. Yeah, if you go back and you look at the experimental result, half filling is here, and you see at half filling, nothing much happens. You have a very smooth dependence, you have a very smooth Hall resistance, you have a very smooth longitudinal resistance. Yeah, seems to be okay. The 1/2 value here is kind of a center. To the left, you start to build all this sequence of plateaus, and to the right as well. Okay, if you deviate from 1/2, then there is a small magnetic field, and that will do whatever magnetic field does to charged particles, namely it will quantize the energy levels. So what we have then is we start with electrons in the lowest lambda level, fractionally filled lambda level. They are mapped onto composite fermions, which fill a Fermi sea at half filling. And if the effective magnetic field is switched on, the energy spectrum is discrete, and you get effective lambda levels in this effective field. You can have excitations there and so on. And you see that if you have an integer quantum Hall effect for the composite fermions, it is exactly at the points where the fractional quantum Hall effect takes place. And it's exactly at filling factors given by this expression. I showed you P is 2 in this case, but it can also be 4 and so on. But if it's 4, then you have to go to much higher magnetic fields. That has not been so well investigated. Okay, just to demonstrate that these particles are behaving like particles in a weak magnetic field, you can look at the focusing experiment. So you have you send a current from here, and you have a drain here, and you do this as a function of magnetic field. And then if you did that below magnetic field, you would get some pattern, which is shown here. Some peaks here, because you get a peak whenever the cyclotron radius matches here. This is the first peak, this is the second peak, this is the third peak, and so on. And now, for the composite fermions, this is now done as a function of the effective field. You get a very similar peak structure, perfect, of course, it's a very similar peak structure with exactly the periodicity that you get down here. That's one thing. The other thing is we have done a lot of work on these systems, taking into account the impurity scattering, and also scattering by the random magnetic field. And this is one example. If you have such a quantum Hall bar with a stripe pattern, where you get geometric resonances here. It's indicated here. This has been measured, so rho xx as a function of a magnetic field. It develops oscillations here. And this is experiment here, broken line here. This is our theory, and it fits perfectly. So this is absolutely well understood. There's another thing that is maybe even more remarkable, and that is if you are in the fractional quantized state, say at the filling factor 1/3, this means that you have 3 flux quanta per electron. And then you can ask yourself, oh, what happens if I have only 1 flux quantum? What kind of an excitation do I have? Well, then you get a quasi-particle, a Volfle quasi-particle, and this quasi-particle, which is 1/3 of an electron, has fractional charge. So there's a charge of 1/3 of an electronic charge. And this has been detected in shock noise experiments. So in this arrangement here, where you have a current crossing over here, and it has been found that the effective fractional charge is indeed 1/3, and they have done the same thing with 1/5, and so on. So it's actually there are these excitations, fractionally charged excitations. Now, according to theory, these Volfle quasi-particles also have fractional statistics. Which is to say they are neither fermions nor bosons, but if you interchange 2 of these quasi-particles, you pick up a phase factor that is not 1 or -1, but it's some intermediate phase. This has not been sort of confirmed experimentally so far, you can imagine, because it's very hard to do such an experiment. And you cannot just interchange two quasi-particles or do an interference experiment. It hasn't been done yet. So that's still out there. Okay? So let me now come to the last part, which is topological properties of quantum matter and topological insulators. This all started with a paper in 2005 when Mealy and Kane and Mealy asked themselves, can we get an integral quantum Hall effect without a magnetic field? Of course, we need some substitute for the magnetic field. And the substitute can be a strong spin-orbit interaction. But that's not enough. You need something more. You need what is called an inverted band structure. So the conduction band and the valence band have to be interchanged. That sounds a bit strange, but let me explain how that works. Let's first look at these pictures here. So in an insulating state, we would have a situation where the electrons are trapped around, say, purity centers. We would have a nice gap here, and in the quantum Hall state, we have the gap and we have the edge states, as we discussed before. Now, in the quantum spin Hall state, we do not have only one edge state, but we have two. Now, this would not be surprising if we had two edge states for both electron spin polarizations, because that would simply mean that we have sort of particles propagating to the right and to the left, and the two currents would just compensate. But what is special here is because of the spin orbit interaction, one of these excitations spin up and the other one spin down. So what you have is, you have spin up moving to the right and spin down moving to the left. Which means there's no net charge current, but there's a spin current. So that's called the spin Hall effect. So now we still have to answer the question, what does this mean? Under which circumstances can we get this effect? And normally we won't get this effect. I mean, we know if we measure this experiment with them, there are always boundary states, and they never lead to anything like this. So what's different? And what's different has been discovered by Fowler and collaborators when they proposed in 1982 that there is a topological classification of crystals that was not known at all before. But this topological classification means that each crystal has a certain topological quantum number, n, t, k, and n, which is defined in this way. So it's an integral over the Brillouin zone, momentum space over the Brillouin zone, of the curl of a certain vector, and this vector is the gradient in momentum space applied to the Bloch function u n k multiplied by u n k star integrated over r. This object is usually zero. But under special circumstances, and as I told you, if the conduction band and the valence band are interchanged, it's equal to 1 or minus 1. And this allows you to distinguish different crystals in a very clean way. Okay? Now, one such crystal is mercury telluride. Mercury telluride has this property. So what you have here is what has been done in the group of Volfle. So they have formed a kind of a hallbar here, which is a quantum well here, thickness D, and a certain width of mercury telluride, embedded in cadmium telluride, I think. And you expect, in this case, these edge states here, spin up and spin down. And here's a little picture that shows you what to expect in the transport. So you have, if you have no inverted bands, you have this situation. So if the Fermi energy is in the middle here, you get, of course, this insulator. You get no current. If you have inverted bands, and the Fermi energy is in the middle, you get an intersection of the Fermi energy with the energy bands here at the edges of the sample, but both up and down, so then you would also get no current, because there's no charge current in this state. I mean, they can't measure the spin current. So in this case, you would get a spin current, but no charge current, and then measure the charge current. Okay? However, if you move the Fermi energy in this inverted band case up, like here, you would get the intersection only with the spin up part here, and you would measure a current, and if you did it, move it below, you get this. Okay. This is exactly what they see. So here is the resistance, this is, which shows this transport effect. So let me start with this. This is a sample which has a thickness of 5.5 nanometers, and they see nothing interesting here, so it's just an insulator. But if the thickness is increased, the system changes over from this situation to this situation, and they find a quantization of the conductance. C2 E squared over H here, which is expected. It's not perfect. You see there's a lot of wiggle here. And why is it not perfect? Well, this is not as robust as the quantum Hall effect, the integer quantum Hall effect. Because anything that flips the spin will destroy it. So any magnetic impurity that you have there will destroy the current, or reduce the current. Okay. But anyway, this is what they saw, and this is considered to be a big breakthrough. Okay, lastly, Majorana fermions. What are Majorana fermions? Okay, this is the unfortunate Ettore Majorana, very talented Italian physicist in the 1930s who disappeared from a ship. Nobody knows what happened to him. It's unclear what he did not arrive at his destination. Okay, but before he disappeared, he made this nice proposal. Then you can have fermions which are their own antiparticle, Majorana fermions. And the question is how to get these fermions. And here topological insulators come into play. If you imagine a 1D topological insulator superconductor, then you will have the following. You will have in the normal superconductor the usual situation. You will have edge states which form in the gap, in the superconducting gap. And these edge states, they always appear in pairs because of modular symmetry. When you have an edge state up here, you can be sure that there's an edge state mirrored down here. They are practically the same particle. However, in a topological superconductor, you can move these edge states to zero energy. When they are at zero energy, then obviously they have to be their own antiparticle. So if you can do that, then you can actually have Majorana fermions in superconductors, and the proposals are to attach a topological insulator to a superconductor. Then at the interface of these two, you would have this effect. It's not yet been done, but I think that people will do that. Now, in a different, somewhat different context, this Majorana fermions appear. They have not been observed, but they are there in superfluid helium-3. Namely, if one is in the A phase, or actually the A1 phase with a spin polarized A phase, where I showed that the orbital dependence of the gap parameter is kx plus I ky, one can have half-flux quantum vortices. The half-flux quantum vortices are possible because of the other part of the order part. Yeah? And in such a system, there can be chiral states that go around the vortex core that are at zero energy. They are fermions. Okay, so this concludes my talk. So let me summarize. So I first discussed that the low-lying quasi-particle excitations of quantum matter within the so-called standard model are transformed and new quasi-particles emerge in ordered states. This is a sort of standard procedure that we have been using for ever since the 1960s, I guess. It works very well. Now, in recent times, we have been concentrating on situations where this simple picture is disturbed by, say, the quantum fluctuations near a quantum critical point, where we get critical quasi-particles, so quasi-particles that have a scaling property, that have a mass, for instance, that scales with energy in a certain well-defined way. There are fractional fermionic quasi-particles in principle, so-called spinons, in frustrated quantum spin systems. Then it's has been long known that the Landau quasi-particles break up into spinons and chargions in 1D quantum wires. And with recent advances in nanotechnology, one can actually see these fractional quasi-particles in the corresponding power law dependencies of the conductors. Then there are exotic quasi-particles in the quantum Hall effect, composite fermions, Volfle quasi-particles, and more recently, the discovery of topological insulators will allow, for the first time, to detect Majorana fermions in superconductor hybrid structures. The role of fractional quasi-particles in higher dimensional systems remains a challenging problem. There have been many proposals of such quasi-particles for the one most important outstanding problem in condensed matter theory, which is high temperature superconductivity. So far, these proposals have not been convincing, but I would say it's not completely impossible that in the end such a solution of the puzzle will come out. From a different perspective, such highly entangled systems, like you have, if you have fractional particles, may play an important role in quantum information technology. And that is what drives the research in this field, I think, mostly over the past few years. Okay, thank you.
Thank you. Thank you very much, Mr. Volfle, for your excellent lecture. And I have One private question.
Oh, no, it's okay. Question.
The lecture is open for discussion, please. Please.
A few words about high temperature superconductors. What is your opinion? Is there a quasi-particle solution, or do we need some extra, theory that we don't have at the moment? Completely new stuff.
For which system?
High temperature
I see. Okay, yeah. Okay, yeah. I can say a few words about it. Okay. This is also, ITC is of course an enormous and gigantic challenge for theory, and it's also driven by psychological and sociological factors. So in the beginning, the field was very much dominated by proposals by Phil Anderson, who was very much in favor of this fractional quasi-particle scenario. And he had some proposals which were a bit, in the end, they did not, in my view at least, turn out to be correct. They were, I think, important because they pointed out that strong correlations are very important in the system. So in that sense, they were okay. In recent times, I would say, in the last 5 to 10 years, there is a certain tendency of theoretical works to go back to a more quasi-particle-like description. Experiments are also improving a lot. And, it's very interesting that in the beginning, when photoemission studies were done and published, it looked like there were no good, well-defined quasi-particles. Now, in recent years, in the recent 3-5 years, it turns out that this is an effect, this is a problem of the experimental capability of reducing background, reducing noise and so on. And I know, experts in this field who claim that the width of the quasi-particle peaks is much, much less, orders of magnitude, factor 10 or factor 100 less than they recorded initially. So now it looks more like there are really good, well-defined quasi-particles. They may be critical in some sense, in the sense I discussed. That's another question. That's possible, so that the quasi-particle mass changes with energy. That's quite possible. But at least there are quasi-particles. In my view, there are quasi-particles. And we'll have to see. The problem with ITC is that it's such a complex system. I mean to say that there are so many different phenomena. And you do not know what is the fundamental phenomenon and what is a side phenomenon. Some people think that charge stripes that have been observed are very important for the theory. Other people say, no, it's only a side effect, not important. Some people say it's a doped Mott insulator. Other people say, no, it's not necessary. You can work with a spin fluctuation driven system. That's okay. So this is, I think what we need is more experiments, more very precise experiments, and then we can distinguish between these different possibilities.
Any more questions? Maybe.
What can move conduction band down and valence band up? What was?
How can a conduction band and a valence band be interchanged?
Yes.
You say? Okay.
Yes.
Yeah. Yeah. It's a question of when you have a strong spin-orbit interaction, then that can distort the band structure very much. It depends on the spin, of course, and the spin up and spin down. So that doesn't mean, this is not meant in the simple picture where you have, one nice band, two nice bands, and they are just interchanged. It's meant in the sense that in portions of the Brillouin zone, in certain sections of the Brillouin zone, they are interchanged. And that's enough. And what you need for this is that when you consider the edge, at the edge, these energy levels are always turning up or down, depending on whether they're electrons or holes, they're turning up or down. And the important thing is what happens there. But it's one particle theory, so you can write down the Hamiltonian, it's a simple calculation.
Thank you. Please.
We continue this topic. If it's just a simple theory, why do we really need topology to explain the properties of these materials?
Oh, okay, yeah.
Is it really needed, or it's just an artificial?
No, I think, no, wait. No, I think it's needed to tell you that it's a robust phenomenon. If it would only be so depending on the details of your band structure calculation, that would not be so good. But if you can say there is a qualitative difference between a topology number 0 and a topology number 1 state, qualitative difference, then you know that this topology state is robust. So if you change the parameters of your model a little bit, it doesn't matter. Still in the same class. That's the important thing.
Yes.
Can you give advice to young people? What is most important